Hello and welcome to another video from Code with Vinay. In this video, we'll be discussing the topic computational complexity with respect to the revised ISC 2024 computer science syllabus. The revised syllabus for the topic of complexity is now on your screen. The topics included in the revised syllabus are the concept of complexity, input size, the importance of the dominant term, constants, and the best, average, and worst case scenarios. If we compare this revised syllabus with the earlier version, we'll find that the main difference is the addition of the word conceptual in the title itself and the removal of big O notation and related components. Addition of the word conceptual indicates a shift in focus towards a more theoretical or abstract understanding of the topic. By specifying conceptual, the syllabus aims to emphasize understanding the principles and ideas behind complexity. Now, big O notation is a mathematical notation used to describe the upper bound of the time or space complexity of an algorithm. Its removal from the syllabus indicates that the revised syllabus will not cover specific techniques for analyzing and categorizing algorithm efficiency in detail, which means a lesser focus on the mathematical aspect of complexity and more on a qualitative understanding. Let's start at the very beginning. What is complexity? In the world of algorithms, it's a measure of how well an algorithm performs as the size of its input changes. Complexity in computer science refers to the amount of resources, such as time and memory, that an algorithm requires to solve a problem as a function of the input size. In simpler terms, complexity is a way of measuring how hard it is for a computer to solve a problem, considering how much time and space it needs as the problem gets bigger. Think of it like a recipe. Some dishes are quick and easy, while others take more time and resources. Similarly, some algorithms are faster or use less memory than others. Understanding this helps us to choose the right approach to solve different problems. In simpler terms, it's a tool to compare two or more approaches to solve a problem in terms of performance. It's crucial to note that when we talk about complexity, we are referring to algorithms, not the entire program. Let's unravel this concept together. Complexity measures how an algorithm performs, particularly focusing on its efficiency and resource usage as the problem size increases. But remember, an algorithm is just a set of instructions, a part of the larger program. Think of an algorithm as a recipe. It's a methodical way to solve a specific problem. A program, on the other hand, is like the entire kitchen operation. It includes the recipe, the chef, the tools, and the environment. While the algorithm is constant, the program is influenced by many variables. Now let us discuss about these variables, the external factors which influence the program. Why can't we directly equate an algorithm's complexity to a program's performance? Well, the performance of a program doesn't just depend on the algorithm. It's also about the programming language used, the hardware it's running on, and even the operating system. These factors are not constant and can significantly impact the speed and efficiency of the program. For instance, the same algorithm might run faster in one programming language than another, or perform differently on a high-end server versus a personal laptop. These external factors introduce variability that makes it hard to predict a program's performance solely based on the algorithm's complexity. Understanding this distinction between the program and the algorithm is vital. While we use complexity to gauge an algorithm's theoretical efficiency, we must also consider the practical aspects when implementing it in real-world program. The goal is to strike a balance, optimizing not just the algorithm, but also choosing the right tools and environment for the best performance. So I hope that this clarifies the difference between algorithm and a program. Now the next thing is, it is about a function of input size. So let's talk about input size. Now let's understand input size, and I'll continue with my analogy of a dish or a recipe. Now, input size is like the number of guests you are cooking for. Just as cooking for 100 people is more complex than cooking for 2, algorithms also get more complex with larger inputs. We'll see how varying input sizes can significantly impact the time an algorithm takes to complete its task. For example, for searching an item in a small array, say of 25 elements, the performance of both linear search and binary search will be more or less the same. However, for 1 million elements, there will be a marked difference in the performance, and binary search will outperform the linear search. Therefore, input size refers to the number of elements an algorithm must handle, the amount of data which you have to process. So, we have seen the concept of complexity, we have also seen input size, and now we'll discuss the dominant term. To understand the concept of the dominant term, let us get back to the recipe example that I took earlier. Think of an algorithm like a recipe and the complexity expression as the list of ingredients. Now, not all ingredients affect the taste equally, right? Similarly, in our complexity recipe, one term has the most significant impact on the algorithm's performance, and we call this as the dominant term. Let us understand this in more concrete terms. We'll be using the bubble sort algorithm as our guide. So let's get started. On your screen is the algorithm for sorting a set of numbers in an array using bubble sort. Have a look at it for a moment to convince that this is the same program which you have been using since class 10th. Let us take a closer look at the bubble sort algorithm, not just as a series of steps, but as a journey with three distinct parts: input, sorting, and display. Our focus? The concept of the dominant term, the part of the algorithm that most influences its efficiency. Every algorithm starts with input. Here we gather the data we are going to sort. It seems straightforward, but the size and nature of this input can significantly impact performance. Next comes the heart of our algorithm, the sorting. This is where the real action happens, and for bubble sort, it's all about those nested loops. They compare and potentially swap elements until everything is in order or sorted. Finally, we have displaying, where we present our sorted data. It's satisfying to see our sorted list, but this part usually doesn't affect the algorithm's performance much. Now let's talk dominant term. In bubble sort, while all three parts play a role, it's the sorting section, specifically the nested loops, that dominates. Why? Because as the input size grows, the number of comparison and swaps in these loops skyrockets, far outpacing the other parts. Imagine adding more and more elements to sort. The time it takes doesn't just increases linearly, it grows exponentially because of our dominant term. This is why it's crucial to understand which part of your algorithm is the dominant term. It tells you how scalable your algorithm really is. Take a look at a graph that illustrates how the number of operations in the bubble sort algorithm varies with the size of input. There are three lines representing different parts of the algorithm: the blue line for the sorting section, the red dashed line for the input section, and the green dashed line for the display section. Now, since the number of operations are same for display and input, the red line for input is hidden behind the green line. The sorting section shows a rapid increase in operations as the input size grows, indicating the algorithm's complexity, while the input and display sections increase in a linear fashion, showing a direct relationship with the input size. Understanding this graph will help you appreciate how different parts of an algorithm contribute to its overall efficiency. In practice, this understanding guides your choices. If you know your application will deal with large amounts of data, recognizing that the sorting part with its dominant term is the bottleneck can lead you to seek more efficient sorting methods. As you explore algorithms, always consider the big picture: the input, the core processing, in this case sorting, and the output. But pay special attention to where the bulk of the work happens, that is your dominant term. And this isn't just academic, it's a skill that will serve you well in optimizing and understanding the real world applications of algorithms. Remember, every part of an algorithm has its role, but the dominant term is the key to unlocking its true nature and potential. So, up till now, we have seen the concept of complexity, the input size, importance of dominant term. Let's talk about constants. Constants in complexity refers to the fixed part of an algorithm's operation that do not change with the size of an input. For example, let us again take a look at our algorithm for the bubble sort. Notice the steps 2 and 3 in bold. Here we are prompting the user to enter the number of elements and reading the input from the user. The time taken to perform these steps is independent and insignificant for large value of input size. In other words, for large input sizes, these constant terms will start to fade into the background and become insignificant. Now let us talk about the best case, average case, and worst case. We are going to understand the best, average, and worst case scenarios in the context of a simple yet fundamental algorithm, that is linear search. Let's see how these scenarios play out. Imagine you are looking for a book in a row of books. In the best case for linear search, the book you want is the very first one you check. It's like finding your keys right in your pocket. Minimum effort, maximum happiness. In technical terms, this is when the target element is at the very beginning of the list. The algorithm finds it instantly, making it the most efficient scenario. Now let us talk about the average case. It's like looking for a book which is somewhere in the middle of the row. You might have to check a few before you find the right one. In linear search, the average case means the target element is likely somewhere in the middle of the list. The algorithm needs to check a fair number of elements before stumbling upon the right one, representing an average number of comparisons. And finally, the worst case. Imagine the book you need is the last one on the shelf, or worse, it's not there at all. In linear search, the worst case occurs when the target is at the very end of the list or absent altogether. The algorithm painstakingly checks each element only to find the target at the last position or concludes it's not there after a complete search. This scenario requires the maximum number of comparisons and represents the least efficient outcome. With this, we have reached the end of this video on computational complexity. I hope it has shed some light on how understanding this concept is crucial for your journey in computer science. Thank you for joining me in this exploration, and until next time, happy coding. Your feedback is valuable to me. I want to make sure that my videos are clear and helpful. You can follow me on the internet on any one or all of these channels.